Hello and welcome back. So, in the last class we were looking at entropy and we looked at Clausius inequality and then we saw the definition of entropy. We also saw how we can calculate differences or changes in entropy between states for a reversible process. We looked at it for solids, liquids and ideal gases and so on. We will look at how to find out properties for steam, essentially entropy for steam. So, we are already familiar with the steam tables. So, I have this open in front of me. When we were looking at the values on steam tables, we looked at the pressure and temperature tables for saturated liquids or saturated vapor. So, we looked at all of these columns, essentially we looked at pressure, temperature, volume and so on. So, the entropy for steam and water is also listed here. We had not used these values so far, but now we know how to use it because we can just read the table, the values of the table for a given pressure and temperature condition. So, for example, if I want to know what the entropy is when let us say the pressure is 0.1 megapascal and it is saturated liquid. So, what I would do is I will go down here to 0.1 megapascal. So, when it is saturated liquid, which essentially on this side of this dome on top over here, what we see is that the value is about 1.3028. I am looking at this value here. SF is the liquid entropy. Saturated liquid has the entropy of 1.3028 kilojoules per kg Kelvin. Saturated vapor, which is on the right hand side of the dome, has a value of 7.3588 kilojoule per kg Kelvin, and the difference between the liquid and the vapor entropy is essentially 7.3588 minus 1.3028, that is the SFG, which is listed over here. We can look at the same on the temperature table as well. So, for example, if I want to know what is the entropy of saturated liquid at 80 degrees centigrade. So, at 80 degrees centigrade the saturation pressure is 0.04 megapascal, which is listed over here. So, I am going to look at this row. The corresponding Vf, Vg, internal energy and enthalpies are here, and what I will go on to is the entropy. So, this says that at 80 degrees centigrade, if I have saturated liquid, the entropy is 1.0756 kilojoule per kg Kelvin for water and the corresponding entropy is 7.6111 kilojoule per kg Kelvin for steam, and the difference in between these two is SFG, which is listed in between over here. And if I was for example on a TV diagram, if I want to know what is the entropy at the same 80 degrees centigrade at a quality of 0.5, which is essentially 0.5 between here and here, then I would find out the entropy in the same way as before. So, I would say S is equal to SF plus X into SFG. So, I would find that out as 1.0756. So, let us say I am exactly halfway across in mass. Sorry. Let us say for the case where X is 0.5, if I want to find out. So, then I say 0.5 into SFG is 7.6111. So, I can calculate this and I can find out the value of entropy. So, essentially this is how we would find out the entropy change for steam. So, we can find out the entropy at each state. There is of course some datum. This assumes that the entropy is 0 at some condition. We can find out that by just going up the table. So, this table is made assuming that the entropy of the liquid, pure liquid, is 0 at the triple point of water, which is essentially 0.01 degrees centigrade. If you use some other tables, it may have a different reference. As long as we are finding out differences in entropy, it does not matter which table we use. If we are interested in absolute values, we should keep in mind that these do not go back all the way to 0 Kelvin. These have some datum which may be different for different set of tables. So, that is about the entropy for finding out entropy for steam. Let us go on to a discussion of a few other processes. So, one of the important processes, as we saw earlier, is a process where we have the entropy being constant during the process, which means that S is equal to constant. In such a case, ds would be of course 0, because if S is constant, change in entropy is 0. We have looked at other processes where something is constant earlier. So, for example, a process where P is constant, pressure is constant, is what we call as an isobaric process. A process where V is constant is what we call as an isochoric process. When temperature is constant, we call it an isothermal process. When enthalpy is constant, we call it an isenthalpic process. When there is no heat transfer, we call it an adiabatic process, and so on. So, a special kind of process is a process where entropy is constant. We call this as an isentropic process. So, ds would be 0 in this kind of a process. What we saw is that ds in general for a reversible process is del q by t. So, if we want ds to be constant, we would have it when the process is reversible and when there is no heat transferred. So, an isentropic process is a process where there is no heat transferred. So, it has to be adiabatic and it is reversible. So, this would essentially give us an isentropic process. So, we already saw what is an adiabatic process. So, in addition to this condition, if the process is reversible, then we have this isentropic process. We can plot all of these processes on TS diagrams. We have already plotted them on PV diagrams earlier in the course. We can also see what they look like on TS diagrams. So, on a TS diagram, the easiest process to plot would be a process where T is constant, because if T is constant, then the value of T should be the same at any given point irrespective of what the entropy is. So, T is constant would now look like a line parallel to the entropy axis. So, we have isothermal processes which are horizontal lines over here. We can also look at all of these processes on PV diagrams because we have already seen them. We saw an isothermal process on a PV diagram would look like different things depending on where we are. So, if we are, for example, in a two-phase dome, then pressure and temperature are both constant and it would isothermal process would be a horizontal line. But if we are considering an ideal gas, then we see that an isothermal process has the equation of PV equal to constant, and that is a rectangular hyperbola, isotherm for ideal gas. Whereas, if it was in a two-phase kind of a region, then it would be essentially a horizontal line. Otherwise, it would be something like this and something like this. So, it depends on what substance it is, but we have that. We have an isentropic process which is ds equal to 0, which means S is constant. So, an isentropic process here would be a process which is essentially a vertical line. On this graph, what we saw is an adiabatic process is of the form PV to power gamma equal to constant. So, if I have some point over here, if this is isotherm, an adiabat will have a steeper slope through this. This is PV equal to constant for an ideal gas, whereas PV to power gamma would have a higher slope passing through this. So, this would be an adiabatic process. If this process is also reversible, then that is essentially isentropic. This is not a straight line. So, we see that on a PV diagram, PV to power gamma equal to constant would be an adiabatic curve, and where gamma is usually greater than 1 for most of the substances we know. So, if this PV to power gamma equal to constant, which is an adiabat, is also reversible, that would be essentially an isentropic curve on a PV diagram. So, we have here the temperature constant, which is PV equal to constant for an ideal gas. It could be also different shapes for other substances. For example, it is horizontal for a two phase mixture and so on. So, we have two of these curves. We can see what the other ones look like. So, we saw some other special curves, for example, P equal to constant, V equal to constant and so on. So, P equal to constant on a PV diagram, of course, is a horizontal line. So, what does it look like on a TS diagram? So, if this is a mixture of liquid plus vapor in equilibrium, then we know that during the conversion process, pressure and temperature are dependent. So, in which case P equal to constant will also be T equal to constant, and both will be within a two phase dome. If I was to look at on a TS diagram also, within the two phase dome, T equal to constant and P equal to constant will be essentially the same, but that is a special case. But let us look at what happens in the case of, for example, an ideal gas, which is of course another special kind of substance. So, we had the TdS relations, which we said is essentially du plus PdV. TdS is du plus PdV, or also we said TdS is dH minus VdP. We can look at what happens for an ideal gas. So, maybe let us take the other relation. This is dH minus VdP. I want to see what a constant pressure process, which is a horizontal line on a PV diagram, looks like on a TS diagram. So, if I take this equation over here, for a constant pressure process, dP is 0, there is no change in pressure, therefore, this term goes to 0. So, I have TdS is equal to dH. What I am interested in finding out in general, if we plot any curve, is to find out the slope of the curve. If the slope of the curve is constant, then I know it is a line. So, for example, y equal to mx plus c, m is the slope. If it is constant, I know it is a line. If the slope varies, then I can see how the slope varies and then try to plot some rough curve. So, this is 0. I want to find out the slope. This is like a y versus x. On a y versus x graph, dy by dx would be the slope. So, here what I want to know, I want to find out dt by ds generally, because this is the slope, and I want to see whether it is constant or it is varying. So, I have TdS, so I have ds over here, I have dH over here, this is enthalpy. So, what I can do is, for an ideal gas, I can replace this as Cp into dt. Then I can rearrange this to get dt by ds. So, dt by ds, which is essentially T by Cp. So, that is the equation, or that is the slope of a constant pressure line. This is at P equal to constant, because I have already removed this out, assuming P equal to constant. So, what I see is that if I assume a perfect gas, then Cp is constant. If I assume generally an ideal gas, then Cp is a function of temperature. If I assume a perfect gas, Cp is a constant, which we often call as some Cp naught, then what I see is the slope depends on the temperature. So, if I am at a low temperature, let us say somewhere here, then the slope is some value, and it is changing as the temperature changes. So, if I am going up like this, as I go up, the slope increases. If I am at some other point here, then the slope is even higher, because at this point the slope is that temperature divided by Cp. At this point the slope is this temperature divided by Cp. So, what I see is, if I am drawing curves like this, I would get diverging lines for pressure equal to constant processes on a TS diagrams. Similarly, I can try to find out what this is, of course, for an ideal gas. I can try to find out what of course, I should not go to S is equal to 0. This I am not intending to show you what happens when this entropy is 0, because we know that will only happen at t equal to 0. So, there is some cut here. So, these are not very close to 0 entropy or 0 temperature. We can see what happens for a constant volume process. If I am looking at a constant volume process, then I will use this equation here, because this has PdV and I know dV is 0. So, then I have TdS is du. In a similar fashion, for an ideal gas, I can write this as Cv dt, and what I am interested in finding out is dt by ds, which is essentially T by Cv. This is at volume equal to constant. The slope of a constant volume line on a TS diagram for an ideal gas is T by Cv. For a constant pressure line is T by Cp. For an ideal gas, I know that Cp is larger than Cv. Cp by Cv is gamma, Cp minus Cv is R. I know Cp is larger than Cv. So, T by Cp, because this is larger and it is in the denominator, T by Cp is going to be smaller than T by Cv, which means the constant volume line has a higher slope than a constant pressure line for an ideal gas on a TS diagram. So, if I was to start at the same point here, the slope for the constant volume line is going to be higher. This also, the slope keeps increasing as the temperature increases. So, V equal to constant would look like this. This is P equal to constant. Starting at the same point, V equal to constant would be even higher slope. So, what I also see is if I was to draw two constant volume curves, these two constant volume curves are also going to diverge. Let me maybe draw it in some other color. So, if I was to draw a constant volume curve, it would look something like this. It has a higher slope than a constant pressure curve, and if I take 2 points here at the same entropy and some 2 other points here, the distance between these 2 points is larger than the distance between the first set of points. So, that is also something which we see. So, this is, for example, a constant pressure curve. So, we have seen that we can draw all of these. We have seen pressure equal to constant, volume is equal to constant, temperature is equal to constant, and we have also seen an adiabatic curve. We have also seen an isentrope over here. So, we can plot these various curves on a TS diagram. What we have not seen is the curve with enthalpy equal to constant, and we will look at that in a few minutes.